Hi, in this lesson, we'll discuss the Smith chart and start with a very basic knowledge of this important tool that all RF people should learn and use. Firstly, you'll learn these basic parameters such as Z, impedance, normalized impedance, admittance, normalized admittance, the real part of impedance, X, imaginary part of impedance, the real part of normalized impedance, the imaginary part of impedance. We have uh, voltage, standing wave, reflection, etc. Then we'll briefly mention those basic equations that construct the Smith chart. Lastly, we'll show how we can use a Smith chart to solve difficult RF impedance matching issues. Smith chart. Smith chart is a tool for visualizing the impedance of a transmission line and antenna system as a function of frequency. Smith chart was invented by Philip Smith in 1939 as a graph-based method of simplifying complex math to describe the characteristics of RF or microwave components and solve a variety of radio frequency problems. So Smith chart is really just a plot of complex reflection coefficients overlaid with a normalized characteristic impedance that's 1 ohm or the admittance of 1 mho. Although calculators and computers can now easily give answers to the problems, the Smith chart was designed to solve these problems remains a valuable tool. So this is an example or an illustration of the Smith chart. Understanding the basic parameters. So our basic parameters are first the impedance is Z. So it is expressed in ohms, and we have two examples of impedance. We have the source impedance or the Z sub S and Z sub L or the load impedance. In order to get the best power transfer from a source to a load, the source impedance must equal the complex conjugate of the load impedance, as shown in this figure. So we have uh, the source impedance R sub S plus J X sub S is equal to the load impedance R sub L minus J X sub L. Therefore, we have R sub S equals R sub L, or X sub S is equal to negative X sub L. If our characteristic impedance is equal to our load impedance, then we can say that there is the best power matching between the source and the load. Usually, in the industry, we often use 50 ohms characteristic impedance for radio frequencies and microwave. And for the cable, we usually use 75 ohms. So we also have as part of our basic parameters the gamma or the reflection coefficient. Reflection coefficient is defined as the ratio between the reflected voltage wave and the incident voltage wave given by the equation shown. So in this illustration, we have the incident wave going to the load impedance and the reflected wave going back to the source. So to plot we plot the reflection coefficient. For example, we have 0.3 plus j 0.5 as our reflection coefficient. So to plot the magnitude of this reflection coefficient, we have to uh, get its magnitude by square root of 0.3 squared plus 0.5 squared. Thus, we have 0.583 and the angle will be 59 degrees. Conversely, uh, we can also do the reverse, that is gamma cosine of its angle, that 0.583 cosine 59 will be 0.3 and 0.583 sine 59 is 0.5. In this particular example, we have this reflection coefficient at point A. Okay. We also have as our basic parameters the normalized load impedance. Okay. So the normalized load impedance, Z is equal to the load impedance divided by the characteristic impedance. That will give us the small letter r plus j and then the small letter x. So we call r as our resistance or the real part of our normalized load impedance and x as our reactance as imaginary part of our normalized impedance. So we call this process normalization if we convert this particular circuit where we have the characteristic impedance and we normalize it, therefore making it 1 on the normalization. And then we will have these particular values of, instead of r sub l, we will have r. And instead of x sub l, we will have x. So in this slide, we have normalized load impedance conversion and the derivation of two important equations. So we will start with our reflection coefficient gamma. It is equal to its real part plus j and its imaginary part. So in essence, we will have z sub l minus z sub o all over z sub l plus z sub o. It is equal to z, our normalized load impedance, minus 1 over z plus 1. And we will substitute the value of z, which is r plus jx minus 1 all over r plus jx plus 1. After a few manipulation steps, we will end with these two uh, equations. So the real part of the reflection coefficient minus those two equations represent two separate sets of impedance circles, the R circles and the X circles, as shown. Okay? For the ease of impedance matching, we will need to add two more parameters plotted on the Smith chart. That is the G and B, or the conductance and susceptance. Okay? So we call Y as admittance in Siemens, that is the reciprocal of our normalized, reciprocal of our load impedance. So that will be on the capital G plus JB. And we call G as our conductance or the real part of admittance, and B, susceptance, as the imaginary part of admittance. So if we are going to normalize the load admittance, that will be Y is equal to 1 over Z is equal to 1 over R plus JX. And after a few manipulation, we will come up with Y is equal to G plus J small letter b. With this, we will come up with two sets of circles, equations of circles. So that those are the G circles and the B circles. Illustrated in this particular slide. Okay. If we put together all four parameters circle plots, that's R, X, G, and B, then we will have a handy and workable speed chart. Okay. Another parameter in this in the discussion of Smith charts is the voltage standing wave ratio. VSWR is a function of the reflection coefficient which describes the power reflected from the antenna. Okay? The reflection coefficient is also known as return loss. So our formula for VSWR is equal to 1 plus the absolute value of our reflection coefficient over 1 minus the absolute value of our reflection coefficient. Each VSWR constant represents a particular circle in our Smith chart. Okay? Remember, if a load is purely resistive, that is, Z sub L is equal to R sub L, but unequal to the characteristic impedance of the transmission line, Z sub O, then the standing wave ratio is equal to our normalized resistance. Okay, so that is VSWR is equal to R. So on the next example, we will discuss how we can use Smith chart in solving several RF problems.